So my name is Anne Currie, and I have been in the software industry for well over 20 years. And the first half of my career, I worked in distributed systems. And so I'm going to talk to you a little bit about the problems, the issues we encountered with distributed systems back then, and what maybe we can learn from them and what we can't learn from them, what we can't take forward. These days, I work for some very pleasant folk out in Amsterdam and in London called Container Solutions. So back in the 90s, when I used to work on quite a variety of stateless and stateful distributed systems, we had a very clear motivation for using them. They were very difficult to develop, they're very difficult to code, they're very, very difficult to operate. But we didn't really have any choice but to use them. And the reason why we didn't have any choice was because the underlying hardware that we were running on at the time was really crap. It was resource-wise, the machines were very small, they had very limited resources. You had limited, on a single machine, access to memory, to CPU. They were slow. And not only were the machines slow, the networks were very slow and very unreliable. And all of this combined to make systems quite unresilient. You had things falling over all the time. We tend to forget how unresilient things were, but if you were around in the 90s, even in the 2000s, you remember that you couldn't run your laptop, your desktop for a day without your operating system falling over. It was just absolutely, things fell over all the time. We got very used to the idea that things were falling over. So we used distributed systems in for what they were originally designed for, which was to increase resilience and performance by spreading out horizontally scaling because we couldn't vertically scale. We just didn't have access to the resources on the individual machines or the networks. But it was horrible. It was hard. It was painful. Operating it in production was absolutely horrific, but it was needed. We had to do it. And then through the 90s and into the 2000s, something changed. Moore's law started to kick in. And actually, machines just got better, got a lot better. Suddenly, you did have those big machines with good resource availability on them. Networks got a hell of a lot better, a hell of a lot more resilient. And suddenly, we didn't only have the option to scale. Our only option was no longer horizontal scaling, using lots of small machines. We now had the option to go for vertically scaling and running things on bigger machines. And the monolith was invented, partly to take advantage of this new world of big machines, which were considerably easier to architect for, and partly because a lot of frameworks like Ruby on Rails, very good frameworks, arrived to exploit this new big server world. So fundamentally, Moore's law kicked in, and it saved us from the horrible experience that we were having running distributed systems and writing distributed systems. And one of the reasons why well, actually, in my talk today, I am going to talk to you about what were the reasons why distributed systems were so difficult. What were kind of the unusual, unexpected error cases associated with distributed systems that used to constantly trip us up. But the interesting thing is that, well, we have the bigger machines now. In fact, machines are growing a lot bigger, still growing at considerable rate. We now have extraordinarily access to fantastically large machines, even in the cloud. So why are we thinking about giving up monoliths? Because we went to the monolith for a very good and sensible reason. That it was much more straightforward to architect monoliths and to operate monoliths. So why on earth are we thinking about giving them up now? Why are we talking about microservices? Have we gone crazy? Because there was a really good reason why we changed. So why on earth are we thinking about moving back? And I will be talking about that today, because I don't think it's always the reason why we think that we're going back to distributed systems again. And it's actually very, very important that we understand why we're doing it, because the reason we think that we might be doing it might be different to the reason why we are doing it, and you would take different architectural choices depending on your motivation. Microservices distributed systems is a very powerful architectural technique. But it's also one that can easily go very wrong, particularly if you don't have a clear idea about why it is you're using it. You can easily, there are so many architectural decisions that you can take, approaches that you can take. It's very important that you decide, you pick a particular one and you know why you've taken it. So what in the 90s used to make distributed systems so difficult? It's something that is both a combination of hardware problems and also people problems as well. So things that haven't actually changed. To a certain extent, it's the laws of physics. In a distributed system, you have more things. You have more hardware components. And when you have more components, there is more that can go wrong. And there's more that can go wrong in strange ways, strange ordering issues that can occur. You've also got the fact that humans, have a great deal of difficulty getting their head around the kind of problems that can occur with a distributed system. And you will constantly hit that. If you're building a distributed system, if you're architecting a distributed system, you will find that your developers don't believe in a lot of the error cases. And we'll come and talk about what effect that might have later. But it is a definite issue. So what kind of problems do we have that are fairly specific to, they're not entirely specific, but they're more or less specific to distributed systems? That your developers, because remember, although we spent a load of time and thinking and pain over distributed systems in the 90s, most of the developers, most of the architects that you're working with now were not around then, so they haven't experienced it. They are children of the long summer of the monolith. They have been working in an environment which is considerably easier to develop in, for very good reason. That's why we chose it. But now they're thinking about going back into a horrible winter is coming style world of distributed systems. They're going to have to think about a whole load of new problems and issues that are going to have to be coped with in any distributed system design of any complexity. So you do need to have a think about it. And the first one is, what time is it? So on a single machine, it's quite easy to work out what time it is. You just call the clock on the machine, and it will tell you what time it is. Within a distributed system, there is literally no such thing as a global time. Now, you might say, oh, well, Google have their global clock that's GPS and all that kind of stuff. Google or Google, that's still not a global clock. That's just made the race conditions a little bit less likely to occur. It's closed the windows, but it's still not really genuinely a global clock. The easiest thing in a distributed system is just to not use the clock as a way of defining order. If you can think about doing things in a way that doesn't use the clock, doesn't use wall time, it might use relative time based on things that happened within a particular session. That's not a clock, though. That's just an incremental counter of some description. But if you can, try not to use the time. Now, if you're a bit unsure about whether this is really true, I had a chat to, I was at a conference a couple of weeks ago, and I was chatting to Datadog, so they do tracing, and I was chatting to their APM engineer and saying, and I wanted to know, I thought, well, they'll definitely be exposed to the issue of different times on different clocks, because it's actually one of the things which is most frustrating in a distributed system is that when you get diagnostics in from different machines, it can be very difficult to work out what order things happened in if the machines have different clock times, and they always do have different clock times. So I suspected that Datadog would have run into this. So I asked them, what kind of a spread of clock times do you typically see across a distributed system that you're tracing in? And they said, well, 10 minutes is not unheard of. And these are systems, these are distributed systems where people are probably making some effort to keep the clocks in sync. But fundamentally, it's very difficult to keep clocks in sync. Every machine's clock will be running at a different rate. When just sending sync messages takes time, even if you're sending sync messages all the time to every machine in your system, which you're probably not, they will start to drift. And it's where they drift, it'll be those, if you're relying on ordering based on clock time to do anything in your system to guarantee consistency or whatever, it'll be where that drift occurs that you'll get bugs that are very difficult to diagnose. So the easiest thing is actually just to be very aware of this and try not to use a global clock as the way that you define order within your system, if you possibly can. There are usually ways that you can find your way around not doing this if you think about it. But if everybody's just if it never even crosses people's mind, then you're going to end up in difficulty. If you think about it, it's not impossible. You can design around it. The next thing is consistency. Now, we do talk a lot. We are quite obsessed at the moment with highly consistent systems. In the 90s, we couldn't have highly consistent systems because that was just way too slow. I mean, a consistent system relies on you effectively locking what's going on across your system, which is extraordinarily slow and does somewhat seem to defeat the object of having a fast distributed system. But if you don't, then really what you're looking at is having states being updated on different nodes within your system and then eventually being merged together. There are different ways that you can safely do that. But you can eventually merge your system together. It's fine, that totally works, but you have to plan for it. Because the upshot of that is that clients querying your system, if you don't know which node they're going to talk to, they can get out-of-date data. They can get stale data, they can get data that predates the response to their previous request, for example. So you do need to be aware of that. You can design around it. You can be less demanding from your client. You can accept a fair amount of inconsistency on your data. But again, you have to plan for it and design for it. If you don't plan and design for it, then everybody's going to have a very rude awakening. So another thing that you need to be aware of is, and plan for and think about at design time, is reliable versus unreliable messaging. When I talk about this, I'm not talking about UDP, I'm not versus TCP. Just let's assume that everything's TCP at the moment. It's not always TCP, but let's assume it's TCP for the argument here. I'm really talking about even where you've got a nice reliable network. If you've got a stateful service over here, talking to a stateful service over here, and they just exchange messages with one another, that is unreliable messaging. And the reason is that these stateless services, did I say stateless services? Stateless services can fall over at any time, because that's what stateless services do, that's what they're designed for, and they can just lose your message. So say message A, service A sent a message to service B, and it's 100% sure that B got the message because it was acknowledged, and then B falls over. A doesn't know what happened to that message, doesn't know if it processed the message yet, it doesn't know if it passed the message on to somebody else, doesn't know if it was halfway through processing the message, has absolutely no idea what happened to that message. As soon as it loses, if A is sending a message to stateless service B, it has to cope with the fact that it doesn't know what's going to happen next. Just doesn't know what's going to happen to that message. Now, there are two potential approaches that you can take to that. You can just design in your systems to accept message loss and duplication and out-of-order arrival. And actually, that is perfectly doable. You can definitely do it. It's difficult, but it's definitely doable. There are lots of examples of, so for example, services that regularly send unreliable messages like video or audio. There are, for all of these types of systems, there are designed ways to handle message loss or out-of-order message receipt. You can take some of those approaches and use them within your own services. There is another approach, which is you say, well, I don't really want to have to design to handle message loss and unreliable delivery and all that kind of stuff, or duplicate delivery, or all of the other things that can go wrong when you're sending unreliable messages. You can put a stateful service in between to hold the message and make sure that it is not lost and it is processed and delivered. So something like a queuing service, a reliable queuing service, you can have your stateless service over here, pop the message on the queue. It knows that the queue acknowledges that it has the message right now. It knows the message is safe. and the queue won't lose the message until B has said, look, I've processed it. B falls over without processing the message. The queue will make sure that somebody else processes the message. So that is a reliable way, when you've got two stateless services, of ensuring that they can talk to one another without losing messages. The downside of it is it's really slow. Compared to just sending a message and handling the message loss, going through an intermediate queue is massively, massively slow. So generally, we didn't do that very often when we were in the 90s trying to make things a bit faster, but it does make things vastly more reliable, and it's more of an option now, particularly when there are quite good managed queue services out there. Another thing to be thinking about is speed of message transfer. And to me, this is a very, very important thing to think about when you're designing a microservice architecture. People often talk to me or ask me or discuss how big should a microservice be? But I think that's the wrong question. It doesn't really matter how big it is. To me, what really matters is what's on the interface. What kind of messages are you passing between one microservice and another microservice? Because internal messages between a component, between threads, or within a single machine are very, broadly speaking, 100 times faster raw, without adding any overhead to them, than messages between two machines that are in any way remote from one another, even if they're just sitting next to one another in a data center. So you've suddenly got 100 times more latency there with processing that message. Then if you add something like RPC, you're adding another tens of, another very considerable bunch of delay. If you're if you're using REST, I think REST is about 20 times slower than RPC. So all of these things add latency into your messages. So you need to be very careful when you're splitting up microservices that you don't have highly latency sensitive messages going between your microservices, unless you want to force those microservices to be co-located on the same machine, or compiled together via libraries, which is an approach I've seen taken. But basically, be careful what the messages are that are passing between your microservices. If they are latency sensitive and they're part of your mainline operation and you really can't afford them to slow down massively, possibly you don't want to have them on your microservice interface. So something to think about. And with all of these things, well, actually, no, I'll come back to that later. Errors. Yes, in a distributed system, the error tooling that you're using against a monolith is probably not ideal for your distributed system. You will almost certainly, everybody I've spoken to who's doing this successfully has had to throw out their old error tracking monitoring systems and put in new ones. And in fact, it hasn't even been a one-time operation where they've just been able to say, oh, right, yeah, I'll get rid of my old one and I'll put in this new one that's just distributed system sensitive and it'll be absolutely fine. They've had to keep replacing them. Because actually, the work we're doing with distributed systems at the moment, it's quite cutting edge. And tools come out that might last you for a bit, but as your scale increases, you quite often, actually, I've seen a lot of people will outstrip the capacities of the tool that they originally produced. So fundamentally what I'm saying is don't get too wedded to your tools in a distributed distributed system environments. You are probably going to have to keep upgrading and replacing them. So, and you'll certainly have to upgrade and replace the ones that you're using for a monolith. Another thing, one of the many other things that are difficult in distributed systems is monitoring whether your service or whether individual services are happy or not. Are they successfully operating? Lots of current monitoring systems monitor end-to-end, end-to-end, point-to-point. So they will give you an alert if a server has fallen over. They'll give you an alert if a web application is no longer responding. But that isn't actually the kind of problem that you want to know about in a distributed system environment. You really want to be designing your distributed system to just come up, and if a server falls over, fine, that's just business as usual. That's a mainline error case. You just have an orchestrator that brings your system back up again. In most cases, just because a server falls over, you shouldn't get woken up at 3 o'clock in the morning. The system should just automatically handle that. So that kind of monitoring and alerting, it's not really actually that useful to you. You do not, it's an error in itself if that server falling over is causing a problem to your system. And the error there is not that the server fell over. The error is that your system went offline. It's an end-to-end monitoring problem. Is your service still available to clients? Is it offering something that your users would consider to be availability or not? I think this is something that is generally now referred to as observability as opposed to monitoring. You want to move over your alerting system to be observability issues. Your users' experience of the system has declined below a certain acceptable point, rather than a machine's fallen over, which shouldn't, if you've designed your system correctly, cause your users' experience of the system to decline below a certain point. That should be all right. So you do need to be thinking about these things quite differently. So when I was, I spent an awful lot of my career first writing distributed systems and then supporting them in production. And one thing I always found, and a large part of my job when I was supporting the systems in production, was taking developers and training them in how to diagnose problems, how to solve problems with the distributed system when it inevitably fell over. And the thing that I found most difficult to convince them of was the level of coincidence that happens every day in a distributed system. You've got a lot of components all interacting, all talking to one another. And the interesting thing is that I think it was one of the earlier speakers today, Chris, I think was talking about how narrative is not a good way of describing what happens in a distributed system. Because it's not really, the narrative is, oh, best case, this happens, this is what's going to happen. But that isn't really what you end up spending your time focusing on once you're actually operating the thing. The narrative, the best case story, everything working happily, you're not even looking at the system when that's happening. When you're looking at the system, it's because something's gone horribly wrong. The narrative no longer applies. And things are too complex, generally, for you to have a narrative around every possible error case. There are ways to handle that, to force yourself to have a narrative around every possible error case, which is actually what he also talks about as well, which is FSMs. Very useful tool for that. Developers hate them, I've noticed, because it forces you, it unearths all of the unpleasant error cases and edge conditions and things. It forces you to think about them. And I have tended to find that in much the same way that developers don't believe in coincidences, they don't really like looking at FSMs either. But yes, so they're going to need to get a different mindset. So they're going to need to be much more, they're going to need to catastrophize a little bit more than they generally do. And it's not surprising that they have difficulty envisaging the error case, the race conditions, the error cases associated with distributed systems, because human life is not, as I said, entirely full of coincidences. It's often, I think, when I was doing this, I found I got better advice from fiction than I did from reality, because reality doesn't contain a lot of coincidences, but fiction is driven by the coincidence. So you'll get much better ideas of things that people have thought through by looking at fiction than you will do by just observing what's going on in your everyday life. And this quote here by Sherlock Holmes and Mr. Spock, I always found to be the single best piece of advice when diagnosing distributed systems problems, that when you eliminate the impossible, whatever remains, however improbable, must be the solution. I can't count how many times we found bugs in systems that we'd show it to the developer, or the developer would be there and they'd say, I just don't believe that could happen. That just couldn't happen. It's way too improbable. But in a distributed system, in a computer, in any computer system, even in just a multi-threaded system, things happen at such a speed and such a rate that your normal human conception of what's likely or unlikely just doesn't apply. You know, 1,000,000 to 1, it's the old Terry Pratchett thing. The 1,000,000 to 1 chance happens 9 times out of 10. 1,000,000 to 1 chance is actually something you're going to hit in production every day. So you do need to be aware of that, but it isn't humanly understandable. So you do need to think about this. Something else that I noticed constantly when teaching developers how to debug distributed systems in production is they do have a tendency to approach debugging in actually what is not the right way. They have a tendency to want to look at the diagnostics. So they'll say, well, just give me all the logs, and I'll look at all the logs. There are a lot of logs. You do not want them looking at the logs to find out whether a problem occurred. If you want to if you want to show them a very good example, this didn't exist when I was doing this, but if you want to show them a very good example of diagnosing complex problems with lots of potential variables, get them to watch an episode of House. You ever watched House? Quite liked House. The idea, so House, a sick person would come into Dr. House's hospital, and no one would know what was wrong with them. They didn't just run a whole load of tests and look at them, the results. In fact, they did. There was one episode where they discussed why they didn't do that. They didn't do that because it didn't work. What they did instead was that they came up with a theory. They said, you know, I think that person has lupus. And then they would selectively choose diagnostics to attempt to disprove that theory. So they would say, okay, well, if they had lupus, then they wouldn't have this result, or they would have this result, or they wouldn't have this result. Let's go and look at those results, see if we can rule in or out that particular theory, hypothesis. And they would rule that out because it would turn out they wouldn't have lupus, and they would then come up with another theory, and they would go through the same process again. And that's actually a very good way of diagnosing problems in complex distributed systems, because there'll be a lot of logs. You don't want people sitting down, starting logs. 3 weeks later, you'll be back, and you will be no further along solving that problem. Come up with a hypothesis, attempt to disprove the hypothesis. I still love this stuff. It was really enjoyable, but it was quite time-consuming, and I never want to do it again. So this is an interesting one. Bugs in distributed systems are driven by coincidence. The main driver of coincidence is traffic. It's things happening on your system, events, dear boy, events. It's messages coming in, it's different things that can possibly overtake one another in ways that you weren't really expecting. There is an issue with this, which is that distributed systems problems, are most likely to happen at times of peak traffic, which are times at which it is most expensive for you to have an outage, a problem in your production environment. You know, when is a traffic-related incident likely to happen to you if you're an e-commerce company? It's probably the middle of the afternoon on Black Friday, when you've got a peak of traffic that's vastly higher and for a long period of time, the time at which you absolutely do not want your system to go out of action. So one way that people handle that is that they just make sure that the system is vastly over-provisioned so that there aren't effectively so many messages per machine. It's very expensive, but that is the way that quite often we used to do it. But nowadays, and this didn't exist for me, and I kind of wish it had, there's chaos engineering. And what I think is interesting about chaos engineering is not, obviously the concept of forcing errors to occur on your distributed system is a very good one. But what I like about it most is the idea that you can force errors to occur at times when it isn't necessarily quite so expensive for you to debug them. So rather than the problems all occurring at times when it will be incredibly expensive for you to resolve the problem because it's the last shopping day before Christmas or Black Friday, you can engineer problems to happen on Tuesday morning to a.m. in February when you really have very low traffic. So it takes the pressure off, takes the cost associated with failures down. And that's actually the thing that I actually very rarely hear talk about, but I'm very interested in the bottom line. So this is what most interests me about chaos engines. So really what I want you to take away, the question I want you to take away from this is, why are you using microservices? Because they are really difficult. They're really difficult. Stateful distributed systems, stateful microservices, very, very difficult to write, very difficult to operate. In fact, I realized, actually, I found this conference quite interesting because so many of the talks, and perhaps that's just because I've been self-selecting which talks I go to, I think almost all of the talks that I've been to so far have been about effectively making distributed systems problems obvious to the compiler. They've been about imposing types that surface some of these distributed systems problems. So people are aware of it and looking for ways to avoid it by effectively just not allowing your code to contain these issues. But that's nice down the road, but a lot of these more esoteric languages are not necessarily going to solve problems that are occurring right now, because right now there are armies of folk going out and building microservices without really understanding what they're getting into. Because when I talked about why we were using microservices in the 90s, I said we were using it for performance. And we had to use it for performance. We had to think about performance all the time. When I talk to people now about why they're using microservices, generally, unless it's like Netflix, they don't tell me it's for performance. In fact, they specifically say, look, I don't mind getting better performance. I'm not going to say no to better performance, but I'm using microservices for the decoupling. I'm using it because then that way I can have teams working individually on microservices without having to interact so much with one another, and I can run my development teams in parallel more effectively. And that is interesting, because what they're using microservices for is to make their lives easier, but they've picked an architecture that can make your life one hell of a lot more difficult. In fact, it's amazing how many people at conferences say, oh, we built a microservices system, and then we had to throw it all away because it ran like a dog, because they had put latency-sensitive messages on their interfaces, for example. Or we built a microservice and what other kind of problems did they have? They just wouldn't talk to one another because they'd got everybody working on their own thing and they had no overall vision for what consistency of APIs or how things should deal with one another, defining what the behavior of each service was. With microservices, I think there is a perception that it's easier. It's not easier. There are certainly ways that you can write microservices to run more slowly and be somewhat easier, and that will probably involve loads and loads of reliable queues that you put in an asynchronous communication. That will run very slowly, but it will be an awful lot easier to develop. If you want it to run at reasonable speed, it will be very, very difficult to architect. Either way, I don't think you can kick your architect out quite yet, because you do need someone to say, well, hang on a minute, no, our overall plan is we're going to use an awful lot of distributed queues. How are we going to, we want to use Linkerd everywhere to simplify. We want to have consistent API formats. We want to all use RESTful interfaces, or we want to all use gRPC. I think everybody does need to make simplifying decisions of commonality around what's going on in their microservice environment. From my experience from the past, this was definitely the case. My experience from going out and talking to a lot of people now, which I do, is that the ones who have become successful have often had to go back and put in a lot of consistency into what they're doing. And they've had to use architects. So, yes, microservices can be absolutely amazing. It's a very cool, and the trouble with it is, it's a very cool, powerful architectural technique. And we are all very inclined to over-engineer. Microservices is something where you can over-engineer like crazy, or under-engineer, or just really badly engineer. And it's very easy to get it wrong. and it requires a considerable amount of experience to get it right. The one thing that we do have now that we certainly didn't have in the 90s, and I really wish we had, was really good stateful services as a service. If I was doing microservices today, I would probably be looking at FAS, although I think that's a little bit, the tooling isn't there quite for that yet. But I'd be looking at stateless, containerized applications, talking to managed stateful services. So I never had to manage or write a stateful service ever again, because I've been there, done that, never want to do that again. That is very difficult to do. So if you want to do this kind of thing, really, really think about using the tools that are available to you. Do not write them yourselves. In fact, so quite a few, I went out and interviewed a few folk recently about their microservices implementations. So the FT, very advanced on this. ASOS, very advanced on this. And one of the things that they mentioned very early is that they never wrote their own stateful services. They always bought them. Their ideal, if at all possible, they bought them hosted. If they couldn't buy them hosted because they weren't yet available hosted, then they would host them themselves, but they were just desperate for them for a solid hosted version to become available so they could move to it, because they didn't want to do this themselves, and rightly so. So if you want to read, well, I'll be around for the rest of the day, always happy to talk about anything, particularly this. If you want to read more about it, there's a chapter in the free ebook that I've just published called The Cloud Native Attitude. You can just Google that and find that. It's available from the Container Solutions website. This talk was also on the new stack. Yes, but that's about it. Yeah, so please do read the book. It's free, and it's not just this kind of stuff. It's kind of a very basic entry-level kind of explainer of orchestrators and containers and distributed systems, and just to try and get people a reasonably straightforward background in it. But anyway, thank you very much for listening today. I hope you have some questions.
Yep. So we have some time for questions.
Hello, hi. Thanks for sharing your experiences. I wanted to ask about the chaos engineering. You mentioned that it might be a useful technique for us. Do you have any ideas? What would you affect in the systems in terms of chaos engineering? What resources and what would you look for?
Oh, well, now you're asking me a question that I'm not qualified to answer, because I never actually used a chaos engine in production. I know that it would have been useful to me. What would I have found? Well, I think I would have focused on the things that did more or less fall over more often. So, I mean, the obvious thing is just to use it to fire a lot more, it's to effectively fire a lot more fake requests into your system, because that's most likely to be what will really trigger expensive outages in real life. So I'd probably start from that. I mean, the classic is you just kill machines, you know, even if you've got, if I were, because I like to do things cheaply, I would start with like a real, you know, a chaos monkey. I would just have somebody in my team who I nominated as the chaos monkey, who on the day that we were going to do the chaos testing, pulled out network cables. Well, actually, if you're in a, figuratively pulled out network cables, turned off machines. Just start easy. But where I have seen this described, something that I thought was a very sensible approach that I hadn't heard before, that I hadn't heard discussed, was that the most important thing is that you tell folk that you're going to do it, and you tell folk what it is you're going to do. So the idea is not actually the system falls over. The idea is that your developers are aware, they believe it. You know, when I was saying that people don't believe it, they don't believe in coincidence, but they do believe in chaos monkeys, I suspect. So really, you know, you just say, well, you know, you don't say, well, you have to fix this because statistically speaking, every VM falls over every 200 days, and we've got 200 VMs, therefore there will be a VM falls over every day. You say, you have to fix it because of chaos monkey. Oh, the chaos monkey. That is my suspicion of what's going to happen when you start talking about chaos monkey. No, just someone running for the door.
I'll ask a quick question. So I think with microservices, And moving from monoliths to microservices, people just kind of gave up on transactions, right? It's kind of like, well, that was a really nice thing, and now we don't have it anymore. So, I mean, what do you do?
Yes, it's just a lot of, to be honest, it's just a lot of sitting back and thinking hard about what the interfaces are between your microservices. You don't have to put an interface in everywhere. You can decide that actually, generally speaking, people aren't, in most cases I'm seeing, people aren't just rewriting everything from scratch with microservices. If you're a successful company, you've got some money coming in from your monolith, and you don't want to chuck it out and go to a giant big bang project where you move over to microservices. That would be crazy talk, frankly. I'm not surprised that people don't want to do it. So they kind of split off. So a lot of the decision making is what you're going to split off. How big should that be? And a lot of the discussions I hear about it are, you split off the bits where there's an awful lot of churn in the code. So you've got a lot of developers who are constantly battling against one another. Part of the other thing you need to be taking into account is what's the message flow going to now be between that monolith and that microservice? Do you want to be? There are certain things you probably won't want to split. And there you might want to keep them all over here or keep them all over here. But that's something that you just have to think very hard about your messages and your interfaces, where they go.
You can do one more quick one. Did you have one?
Some people have used introducing microservices as a way to go to support multiple languages, often because someone wants to play with a new language or use a new language. Is that a good reason, or have you seen good outcomes with that?
Sorry, leading question there. Yes, I am. Somebody made a joke to me earlier about a mother saying to their child, "Go and find out what your brother's doing and stop him." Developers, go and find out what your developers are doing with microservices and stop them. If they're using it because it's cool, because they just want to muck around and do something dangerous in production, like use a language that they don't necessarily know how to operate or support, that's not, for me, a good reason for using microservices. I don't object to the use of to using microservices because of the radical decoupling and the ability to parallelize your teams. I can see the logic in that. I'm just saying that if that is your logic, you need to be aware of it and you need to make architectural choices accordingly. But for me, because it's cool, because I get to play with some technology danger-free, is not a good reason at all, and it should be stopped. Under my watch, it would be stopped.
Okay, let's thank the speaker again.